Okay, so thank you. So I am going to finish with this last lecture by trying to put all together and to get some idea on the proof, at least that if you take a truly varying family of holomorphic curves, then the monodromy is infinite and irreducible in the sense that there is no multi-curve which is invariant by the monodromy representation. I'm sure that I will not have time to explain to you why this statement about the monodromy implies a geometric model conjecture. But I think that just this statement about the monodromy is extremely interesting in itself. So let's try to arrive to there in this last lecture. So I will need to make a little complement about my paragraph on the projective structures on Riemann surfaces. So what we did this morning was to show that if you consider the space of projective structure, so CP1 structure on a given Riemann surface, so this is isomorphic, so biholomorphic to a complex affine space of dimension 3G minus 3 if the Riemann surface is compact of genus G, right? It is isomorphic to the, more precisely to the space of holomorphic quadratic differentials on the curve. And this isomorphism is given by the Schwarzian derivative. So I would like to say something which will be really important for us in what follows. So namely, what we could call univalent projective structures. So say a projective structure is univalent if its developing map, so maybe so the developing maps of the projective structure are the maps D in the definition, so the map which is defined, so the holomorphic immersion defined on the universal cover of the surface, which is equivalent with respect to some representation. So the map is called the developing map, and the representation is called the holonomy of the structure. Maybe I didn't say that this morning. So if its developing maps are injective, and I will sometimes call for injective univalent because of historical terminology. And in fact, so what I would like to say now is that if you consider the set of univalent projective structures inside the set of projective structure on X. So X is a Riemann surface. So this is compact, say, Riemann surface for genus G. So this set is a closed, bounded set. It's a compact set in the set P of X. Okay. So it's theorem. So this set is compact. So the fact that it is closed, so it is closed because uniform limit of injective holomorphic maps are injective, right? And the fact that it is bounded, so it is not at all trivial, it is due to the following lemma. I think it was first proved by Grönwald, but I'm not completely sure about that, so I'm going to put it this way. So the lemma shows that if, so let f of z, so let's say f from the disk to the Riemann sphere be injective holomorphic map, then the Schwarzian derivative of f is bounded by a universal constant. I think it is 4, but let's say C universal. I think it is 4 times the hyperbolic metric on the disk, so times dz. So this is a universal constant. I think it is 4, as I said, but I'm not sure. So let me just, you can prove that, and I let you the computations, to make the computations as an exercise. So in fact, so what you can do is that you can, up to post-composing the map by a Möbius transformation, you will not change the Schwarzian of the map. And of course, you will not change the fact that it is injective. So you can assume that f of 0 is equal to 0. Derivative of the map at 0 is 1. And second derivative is 0. You have 3 conditions because Möbius group is 3-dimensional. So you can assume that the map has this form. Z plus A3 Z squared, Z third, sorry, plus etc. And if you put the map in this form, I think the Schwarzian derivative is going to be approximately A3 times 6 or times something, but time universal constant. So I think it's going to be A3. 6 times A3, I think. And 0 is 6 times A3. So you need to prove that A3 is bounded by a universal constant. And the way you can do that, so in general, it's better to take, so to make a certain transform, so consider this map of W, which is, I mean, you take the same map, but you replace using 0 to infinity. It's going to be better for the computation then. So, so this map will take this form, W plus B1 over W. Right? And here B1, if I'm not mistaken, is minus A1. A3, sorry. So you need to prove that for this map, so you assume, so this map is defined on the complement of the unit disk, of the closed unit disk, to the Riemann sphere, right? And since it sends a point infinity to infinity, I mean, for a value which is different from infinity, it's finite. Okay, so it's a holomorphic map from exterior of the unit disk in the complex number to the complex number. And so you need to prove that B1 is bounded, right? And so my claim, and I let you prove that as an exercise, it's kind of just of Stokes' formula, compute the array So of course, so just do a picture. So you have the exterior of the unit disk. G maps this domain to something, so to the exterior of some subdomain in the complex numbers. So try to compute the array of this domain, right? And what I claim is that there is a formula, which is that so the array of the exterior of the image of G is equal to 2 pi times 1 minus B1 squared minus 2 B2 squared minus etc. This you can just prove by saying that the array of this domain is, by Stokes' formula, is an integral of a certain one form on the boundary of the domain. This one form, you can express it exactly using the function g. And you make Fourier analysis, and you prove that you get this formula. And so with this formula, you see that modulus of B1 needs to be less than 1 because this series has positive terms, and I mean, the array is a positive number, so you need to have B1 less than 1, right? So this proves the lemma. And so now you have, so this lemma will tell you that if you put on the set of quadratic differentials the norm, which is a uniform norm with respect to the hyperbolic metric on the curve, so the set of projective structures for which, of univalent projective structure, has Schwarzschild derivative which are bounded by this constant C universal. So this set is bounded. And so the theorem is proved. Okay, in fact, we will get, I mean, the description of this set is very difficult. We will now take some time to describe some elements of some projective structures that are univalent using the theorem of Mordell that I was describing. Okay, so now I'm going to prove the theorem by Bers that says that there exists a holomorphic embedding of Teichmüller space in complex affine space whose image is a bounded open domain in C3G minus 3. So to do that, we will use the theorem of Mordell. So we will use this Beltrami equation that is solved by this theorem. And the first thing I'm going to do is I will consider gamma a Fuchsian group. So in PSL2R, which is the group of holomorphic automorphism of the half plane. So this is a Fuchsian group of genes G, right? And I'm going to take as a reference surface for the Teichmüller space, I'm going to take SG, the reference surface, just being defined by H over gamma. So this is the reference surface. This will be the reference surface. And I'm going to denote by H plus the upper half plane and H minus the lower plane, right? So is it clear what is the upper half plane for everybody? Okay, so let's just say it is a set of complex number with positive imaginary part. Okay, so this H minus is a set of complex number with negative imaginary part. And so we will do the following. So we want to embed Teichmüller space into an affine space, and so we will use we will embed in fact Teichmüller space in the space of projective structure on a certain Riemann surface, which is so what I'm going to do now is that I'm going to play the following game. I am going to embed T of x plus, so the Teichmüller space of x plus, that I am going to think as the set of Beltrami coefficient on x plus mod relation, being image of each other by the quasi-conformal map isotopic to the identity. And I will embed that in the set of projective structure of the surface, say, x minus, which is the quotient of h minus by gamma, the Fuchsian group. So this is another Riemann surface, which is the conjugate of x. So say this is h plus over gamma. So how this game is going to, how we'll get that? So let's be a Beltrami coefficient on x plus. So that defines for me an element in the Teichmüller space. Denote by mu tilde the lift of mu on the universal cover of x plus, which is upper half plane, and 0 on the lower half plane. So on h minus. Okay, so here is a Riemann sphere. So here is a real projective line, upper half plane here, lower half plane here. So I define a Beltrami coefficient, which is just the lift of mu on the upper half plane. So I change the complex structure here. I have a, say, fields of ellipses that have changed on the upper half plane, but here on the lower half plane is just a classical complex structure, classical spherical fields, right? And now I can solve the Beltrami equation. So by Mordell's theorem, there exists a unique phi of mu, quasi-conformal homomorphism, associated to this Beltrami coefficient. Namely, it satisfies that d bar of phi mu over is this Beltrami coefficient, and moreover, phi mu fixes the point 0, 1, and infinity. It is unique, and it depends holomorphically on the Beltrami coefficient mu, right? So this phi mu is has the following property: is that because mu tilde is invariant by the Fuchsian group gamma, right? So in fact, by unicity of this phi mu is going to be equivariant with respect to a certain representation in the group of automorphism of CP1, right? So because mu tilde is gamma invariant, I claim that phi mu is equivariant with respect to a certain representation rho mu from gamma to PSL2C. Why is it true? Because if you take phi mu precomposed by an element gamma in the Fuchsian group, this is also a solution of the Beltrami equation. But the only thing which differs is that you do not fix 0, 1, infinity anymore. So you can just modify by post-composing by a certain map in the group, in the Möbius group, so that this will fix 0, 1, and infinity. This map I denoted by rho mu gamma inverse, so that this is equal to phi mu. Right? It exactly gives you that phi mu is equivalent with respect to the rho mu representation. Right? So here you see the power of the solution of this Beltrami equation, and the reason why I bother you with measurable Beltrami coefficients, because a priori you say, okay, you're completely crazy to consider this coefficient. But here, let me just emphasize on that point here, because generally what is going to happen is that the image quasi-conformally conjugates the group gamma to the image of the representation rho mu, which is a Kleinian group. It is a discrete subgroup of PSL2C. And this Kleinian group has the problem. So this phi mu, so I'm just saying what is going to happen without proof. But so in fact, if you look at what is called the limit set of the Fuchsian group, which is a projective line, this projective line is mapped by phi mu to a curve which is a simple closed curve, but it is just continuous. It's completely fractal in general. So a priori, this phi mu is going to really completely distort the differentiable structure in this sense. So of course, you could take mu differentiable on x, right? No problem. But you put 0 on the lower side. So of course, you have a strong discontinuity of the Beltrami coefficient here, right? It's still measurable, it's still bounded, but and the effect of this discontinuity is the fact that the phi mu is not at all differentiable on this curve. And in fact, the curve is mapped to a curve of completely fractal curve. Okay. So this is, you can see here all the power, and I think it answers some questions about why we are considering some measurable Beltrami coefficients. A priori, at the beginning, we don't expect that this is of any utility, but we see it here. Okay, so now, so this is good. So all these things vary holomorphically with respect to the mu parameter, right? So we construct holomorphic functions, namely, for instance, this representation. Those are matrices that the coefficient depends holomorphically on mu, right? Everything depends holomorphically on mu because of the holomorphic dependence of the solution of the Beltrami. And now, what is the projective structure? So I say that we get a projective structure on the lower half plane, and the projective structure is just given by the restriction. So define so B is the Bers map. I want to define a map that I'm going to denote by B. So I'm going to denote it by Bers because otherwise it could be Beltrami. Say Bers of mu by definition is a projective structure defined on the lower half plane, defined by the restriction of phi mu to H minus. Because the Beltrami coefficient is 0 on H minus, so this map is holomorphic, and it is equivalent with respect to representation, so it defines the projective structure. This lies in P of X minus. And in fact, so that's it. So this projective structure is univalent, right? Because phi mu is just a homomorphism, so it is univalent. So in fact, the image of this map takes values in this compact subset that we just described before. The map is holomorphic. We just said that. So of course, this phi mu depends holomorphically on the mu parameter. And this map is injective. So why this map is injective? So I'm not going to bother you with the details. The idea is that just, in fact, you recover. So if you know phi mu, so you know the image of phi mu here. So you know the domain which is the complementary of the closure of phi mu, which is the domain, which is the image of the lower half, of the upper half plane, right? And the quotient of this domain by the group rho mu, which is the holonomy of your projective structure, is just the Riemann surface you started with. Okay, so you record the information of the element of Teichmüller space you started with. I mean, this is completely encoded in the projective structure. Okay, so now it is so this is the Bers embedding. This is really a very nice object and powerful object, as we will see now. Okay, so. So all the proof, so now I really have almost all the thing to get the proof that of the theorem about the monodromy that I announced. I'm going to, sorry? Holomorphic? Yes, it is holomorphic because phi mu depends holomorphically on the mu parameter. So the Schwarz derivative also depends holomorphically, and you get a holomorphic map. So this is really the interest. In fact, the idea of the Bers embedding, in a sense, so we say that every, this is the second uniformization theorem of these lectures. So there is this first uniformization theorem where you uniformize a Riemann surface by a Fuchsian group. But of course, the Fuchsian group is something in a real character variety. So the set of representation of a surface to the group PSL2R, mod conjugation. So this is a real variety, and it has, a priori, it has no complex structure. So you to get something holomorphic. So the idea is to go to the complex world and to complexify the situation, to take the representation in PSL2C. And so if you do that, I mean, this is the first idea in the sense of Bers. So to allow in the group PSL2C.
Convex in the formula you come
this formula. I understand the question. I'm sorry. Take this formula, yeah, and.
Embedding of Teichmüller space into C feature minus 3 is bounded domain. Such formula assumes that the domain is.
Okay, I understand your question. So is your question related to the fact that the image is open? Yeah, there is something to be said. I forgot to say. So if this is your question, this is a very good question, because so I said we get a holomorphic map from Teichmüller space to this affine space, which is of dimension 3G minus 3. And we didn't say anything about the fact that the image is open, but this is just the theorem on the domain. So if you have so we know that Teichmüller space is, I recall that Teichmüller space has dimension 6G minus 6, real dimension 6G minus 6, right? So you get a map from if you have an injective map from between two manifolds of the same dimension, the image is open. And even in injective homomorphism, an injective continuous map.
Why is it bounded?
Sorry?
Why is the bounded domain?
So this is bounded because this projective structure is univalent, right? So phi mu is a homomorphism on the whole Riemann sphere. So in particular, if you restrict it to a subdomain, it is injective, right? So this developing map is injective. So it is a univalent projective structure. And we proved just before that the set of univalent projective structure is compact. Right? So this is the reason. Yeah, so I'm going to So now what is going to be very important will be to understand what happens for the Bers embedding when you go at infinity in Teichmüller space, when you degenerate. So you take the image of the Bers embedding for a sequence of Riemann surfaces that are degenerating, right? And this will be very important for the argument. So let us try to spend some moment to understand how this degeneration and how all this works. So let me just make a picture so that you can have a feeling of what happens. So in fact, the idea is that for the Bers embedding, the idea is the following. So let me just draw the quasi-Fuchsian group. So quasi-Fuchsian group is just the image. So one of these groups which are quasi-conformally conjugated to a Fuchsian group. So the image, so the holonomy representation of these projective structures that we just defined are quasi-Fuchsian group. So here I am drawing what is called the limit set of this quasi-Fuchsian group, which is just the image of the real projective line by the quasi-conformal conjugation. And in fact, here we have our surface x minus on the bottom. So say the quotient of the bottom here gives you the surface x minus. And upstairs we have our element in Teichmüller space. So this is the mu given by the Beltrami coefficient mu. Just I'm going to denote it by y with an index n because I'm going to take a sequence of Riemann surfaces that are degenerating. So assume that the degeneration, so we gave examples of the degeneration of Riemann surfaces where we have a simple closed curve which is pinched at the limit to get a singular algebraic curve. So just take this example to see what happens here. So suppose in this example, this is this curve, this family of curves that are pinched at the limit. So here at the limit, you get this picture. What is going to, so maybe I should make the picture and draw the limit set in the plane. So just I'm going to represent the Riemann sphere as a set of complex number plus the point at infinity. And here is the limit set. So it's a priori it's a Jordan curve which is fractal. At the limit, this fractal curve is going to become a more complicated fractal set. For instance, it would look like this kind of fractal sets. So in fact, let me just tell you what happens without proof, just to get a feeling. So I'm going to stop here. So the thing is that you can lift this curve to the universal cover of Yn. So here is a hyper half plane, which is the universal cover of Yn. If you lift this curve, you see a countable family of of curves in the universal cover. And in fact, this picture here is just that all these curves has been pinched at the limit. So you just identify, to get this fractal set, you just start with a circle and you identify the extremities of all these curves to each other. So you get here, you get one point here, or here you would get this point here, etc. So you get this this picture. So of course, x minus in this picture is just the exterior of all these things. So at the exterior, if you take the quotient of the exterior of this domain, just of this fractal set, in the complex number by the group, you get the Riemann surface x minus that has not changed, right? So x minus in the construction does not change. So what changes is the conformal structure of the upper half plane. Right? So this is one of the degeneration that you can see, and I make here the observation that in fact at the limit, at the limit you still have a univalent projective structure, right? Which is the quotient of the exterior of this domain by the group you get. And this univalent, so the holonomy, so the group you get, the holonomy representation that you get, has a very important property here, which is called, it has some accidental parabolics. So namely, in fact, if you look at the image of this curve at the limit, so for each end, the image of this curve is a loxodromic transformation of the Riemann sphere. So it has two fixed points and it has a hyperbolic behavior. But at the limit, the two fixed points become the same. So the two fixed points are the extremities of those curves. At the limit, they become the same, and the map becomes a parabolic map. So namely, it has a unique fixed point, and in some affine charts, it looks like a translation. So in fact, in this kind of degeneration, we see at the limit something which is called okay. So here, just maybe to make clear the situation, I'm looking at the Bers embedding of Yn. So this is a projective structure, which is so Yn is degenerating, tending to infinity, and this lies in the compact set. So I can look at a limit value up to taking a subsequence. And what I will get is this picture here. I will get a projective structure because I'm in the space of projective structure. And this projective structure will look like what I described here. So namely the quotient of this, the exterior of this fractal set by a certain Kleinian group. And in this situation, we see an accidental parabolic. But of course, you have also examples where, so let me just draw another possibility, which is the possibility that, in fact, Yn does not degenerate in this sense. So it is possible that in Teichmüller space, the Yn degenerate in a sense that, for instance, all the lengths of all curves, of all homotopy classes of curves in the reference surface tend to infinity. Right. So, for instance, here we have an example where we have a family of Riemann surfaces where the length of some simple closed curve, hyperbolic length, tends to 0. But in general, in the degenerations of Riemann surfaces, generically, when we take an element which goes to infinity in Teichmüller space, it's not this phenomenon that occurs. It is that all the lengths goes to infinity at the same time. So we have some examples. So in fact, the fact that all the lengths tend to infinity at the same time, the picture is different. So the thing is that what is going to happen is that the domain which is inside here, so for degeneration where yn has this property, so the domain which is inside, so representing the universal cover of yn, is going to shrink to a very, very thin domain, and at the limit tend to a dendrite, so a fractal set which is a dendrite. So let me just give you an example. So you will see some domain which is, so the domain which is inside the component will going to become much thinner and thinner. So I'm going to stop now. And at the limit, you see something which resembles that is called a dendrite. So it is a fractal set looking something like this. Okay, so we also still have here that the quotient at each moment, the quotient of the exterior of the domain that I am drawing gives you the surface x minus, and this is the same. So the exterior of this dendrite here gives you x minus, but the domain which are inside disappear completely at the limit, right? In fact, in this situation, what happens is that the hyperbolic metric inside such a domain which is very thin is going to tend to infinity with respect to the Euclidean or spherical metric, right? So you can prove that. And in fact, if this kind of degeneration is happening, this will prove that what I said, the length of the non-trivial homotopy classes of curves in Yn tends to infinity, because the hyperbolic metric in this really thin domain tends to. So in fact, I just gave you two pictures to explain a result I'm going to draw on the board. Yes?
The volume of a hyperbolic surface of a given genus stays constant.
Yes?
So how can all the curves at the same time go to infinity?
Well, so for instance, if you take a pseudo-Anosov map, okay, you just take the image of your hyperbolic structure by a pseudo-Anosov map, you see that all the lengths of the curve, so the length of the image of a given curve, are all tending to infinity, right? So
Uniformly the same time.
Okay.
Uniformly the same time.
It's not
They
at the
will
same time.
eventually get very long.
Yeah, not at the same time.
But this
not, yes, maybe as,
yesterday as well when the questions talking. They eventually all go to
You're right.
Not really the same time. Some eventually.
That's right.
They will always end up.
So the statement is that for each homotopy class of closed curve, the hyperbolic length tends to infinity, but of course, the moment where it becomes really large, it depends on the choice of the homotopy class. So let me just state a result. Which is that essentially these two phenomena are exactly what happens. So this is a combination of a theorem by Maskit and another theorem by Abikov that I am going to make in the same statement, which is that suppose, so I hope these pictures are going to help to understand this statement. So it's a theorem by Maskit and Abikov. I hope I'm not mistaken the orthograph here. So this is that suppose that, so let me just see how to state that. Okay, suppose mu n tends to infinity in Teichmüller of x plus, right? And in such a way so that the associated projective structure Bers of mu n tends to a projective structure towards a projective structure phi infinity, right? So this is going to be a univalent projective structure, right? So either phi infinity has accidental parabolics, or the length, so or for any non-trivial homotopy class of loop in the reference surface, so C, what I call C, have that LC of mu n tends to infinity. Right, so the hyperbolic length of this loop tends to infinity for any homotopy class of loop, trivial homotopy class of loop. Okay, so let me just give you, because I don't really know what is accidental parabolic, let me just give a formal definition so that the statement is clearer. So if phi is a univalent projective structure, say phi has an accidental parabolic, if its polynomial representation contains a parabolic element. So what is a parabolic element? So this is a map M in PSL to C. It's parabolic. If the fixed point set of M is, say, 1 point, consists of only 1 point. And in fact, it looks like, so the action of this parabolic map on the Riemann spheres, so it looks like you have this point and you have the, say, the pencil of circles passing through this point. You have a certain pencil of circles like that, which is invariant by the map, and the map preserves each of these circles, and the iterates of the map tends to the fixed point in plus and minus infinity. So it looks like this. And in fact, there is a characterization of parabolic transformation in PSL to C, which is the fact that, so M is parabolic, an algebraic characterization. So it's unipotent in a sense, for those who prefer this terminology. So M is parabolic if and only if M is different from identity, and the trace to the square of M. So I take trace to the square because I'm considering something in PSL to C, so something which is defined up to sign. So the square of the trace is well defined. So this square of the trace is equal to 4. So namely, the examples of a parabolic map is just the one given by this matrix. This typical example of a parabolic matrix. Yes?
Can you say again, in this if I have a sequence where it goes to infinity,
n tends to a high infinity?
Yes, because
Is it part of the hypothesis? Or?
no, here, but you can, what you say is true. You can always say. So the thing is that if mu n tends to infinity, you consider the. So here in this statement, I suppose Bers of mu n tends to some point, phi infinity. Because I use this phi infinity in the conclusion.
It's still univalent.
And it's still univalent because the set of univalent projective structure is closed, right? So these Bers of mu n are univalent, right? We saw that. So this phi infinity is also univalent.
But it's also part of the conclusion. You don't need to suppose that it converges. You know that a subsequence will converge to such a point.
Yes, but I want to use this phi infinity in the conclusion of the statement. So just I state it like this. But you can say that you can start. Okay, so what you can do is you start with any sequence which converges to infinity. Up to taking a subsequence, you can assume that Bers of mu n tends to something because the set of univalent projective structure is compact, right? And then you have this conclusion, right?
By the way,
Yes.
Can you characterize when this Bers of mu n does converge? Is it what the conditions?
Right. So this has been studied a lot by many people. First of all, Bers has various works, and there is a very general theorem by Thurston when, in fact, he moves both of the complex structure, so the one of the bottom and the one of the top, and he's able to understand when the corresponding quasi-fixed group is going to converge to something at infinity. And so all these questions have been solved, I think, but it's very difficult. So I think I draw some these pictures. I think are the ideas of the proof. So to prove that, so if there is some component, so if the upper component does not completely degenerate, in fact at the limit you will have a component which remains, and then you have to appeal to a theorem by Alfors, the finiteness theorem by Alfors, to really be able to prove that there exists an accidental parabolic. I will not do the argument here, but I just gave an example where you see with your eyes accidental parabolic appearing. But this works like that. And if the positive component shrinks completely to dendrite, so then this is just an estimate on the hyperbolic metric on really thin domain in the plane, which enables to have this second conclusion. So the hyperbolic metrics, the idea is that the hyperbolic metric on the domain tends to infinity, so the length of the curves needs to go to infinity also. So this is more or less the idea of the proofs. But of course, this is kind of deep, and I have not enough time to give the details. But let me just finish by stating this theorem about the monodromy and trying to give you the final argument, and I will stop. So this statement about monodromy is like that. So it is a statement that has been proved by Shiga in the 80s or beginning 90s, which is the following. So assume XB is a truly varying family of Riemann surfaces over of compact homogeneous at least 2 over finite type base. So B is a Riemann surface of finite type. So this is a compact Riemann surface minus a finite number of points. So then the monodromy representation of this family is infinite and irreducible. So infinite means that the image is infinite. So it's an infinite subgroup of the modular group. And irreducible means, so let me just recall that monodromy representation is a representation that I am going to denote by mon from the fundamental group of the base to the modular group. Right. So the image of this representation is infinite, and irreducible means that, so this means that there is no multi-curve invariant by the representation. So I should say there is no homotopy class of multi-curve, to be precise. So a multi-curve is a finite, so it's a finite set of disjoint, simple closed curves, or even, in fact, we will prove more than that, but anyway. So it is a finite subset of simple closed curves that are, each of them are non-homotopic to a point. Right. Okay, so let me just prove this using what we just using the material that we developed before. So in fact, you can think of your family as being given by a holomorphic map. So the family XB is so. Say, I would say it's classified, but it's given by an equivalent, so a mon equivalent non-constant, because it is fully varying holomorphic map little h from the universal cover of B to Teichmüller space of genus G. Right? So you fix, so say you fix the base point on B, you fix a marking on the fiber of this base point, and then you deform your base point using a path, and you follow the marking. Okay, and so it gives you a way to mark the fibers of your fibration. But of course, when you come back to your original position, the marking has changed. So you get another Riemann surface, which is the image of the original one by an element of the modular group, which defines the monodromy representation. So you get this map, which is holomorphic, right? And now compose this map by the Bers embedding to get a map to a bounded domain in C and C3G minus you get so big edge, which is just Bers composed edge from universal cover of B to but in fact, you go inside this compact set of univalent projective structures. So this big edge is a bounded holomorphic map. This one is. So you can So we are going to apply the Fatou lemma, which says that if you have a holomorphic map or harmonic map, which is bounded on the on the unit disk. So here B. Okay, so I should first say that B needs to be a hyperbolic Riemann surface, because otherwise it would have a bounded holomorphic function, which is violates the Liouville theorem. So it is a hyperbolic Riemann surface. So you can identify the universal cover of B with the unit disk. So this has a bounded holomorphic function, non-constant holomorphic function. So this is diholomorphic to the unit disk by the uniformization theorem. And so you get a map which is defined on the unit disk to C to the power 3g minus 3, which is bounded. So you can apply Fatou lemma. So the map H has say so Fatou lemma. I don't know how to say that in English. It has H has limits in angular domains for almost every point on the boundary. So if you take a point in the boundary, which is generic with respect to the Lebesgue measure, and you take a domain which goes inside the unit disk, then the function H is going to have limits. So if you take a sequence of points tending to this boundary point and that lie inside this angular domain, then the function H is going to have limits along this sequence of points. Okay? So has, say, I don't know. I'm sorry, I'm kind of tired now. Limit values. So if zeta is a point in the boundary of the unit disk, so then if I see this function H as a function defined on the unit disk, I will have an extension of H which is defined on this point psi, right? So yeah, H of psi will exist. Is going to be defined for almost every point in the boundary. So now this H of psi is a univalent projective structure, right? And what we want to prove and what we will prove now is that these boundary values correspond to univalent projective structures that do not have accidental parabolics. And so the claim is that homogeneity, this H of psi has no accidental parabolics. And the reason is very simple. Because, so, in fact, for each point, so this is a point in the space of projective structure. So for each point in the space of projective structure, we have a projective structure, but also we have a holonomic representation that I denote by rho of the point. So this is a representation from the Fuchsian group gamma to PSL to C, which is well defined up to conjugacy. This is a holonomy. Of the projective structure H of any point say. And what I want to prove is that if I take an element which is different from the identity in gamma, then this holonomy representation maps this element to an element which is not parabolic, right? But we have seen that being parabolic is saying that the element is different from the identity, and that the trace is equal to 4. Trace to the squared is equal to 4. So we need to prove it is different from the identity and that the trace is squared is different from 4. The fact that it is different from the identity comes from the fact that if we have a sequence, I mean, it is possible to prove that the limits of the holonomy representation are still discrete. This is what is called the Zassenhaus lemma, and I will not comment more about that. So this is something which comes from the fact that a limit of faithful and discrete representations is still discrete and faithful. But the fact, so what is more difficult to prove a priori is to see that there is no accidental parabolic, because we saw that it is possible a priori that it happens. And so we need to prove that the trace square of rho of H of psi is different from 4 almost surely. So I take a gamma which is different from the identity in the Fuchsian group, and I need to prove that when I map this gamma by the representation rho of X of psi, it's not parabolic. So this is different from 4. But you see that this function, if you make the xi variable vary in the unit disk, is a holomorphic function. And so the thing is that it is a consequence of the fact that if you consider a point which is inside the unit disk, all the representations are quasi-Fuchsian, or they are all quasi-conformally conjugate. So gamma is mapped to a loxodromic element, so an element having two different fixed points. So it is loxodromic. So in particular, the trace squared is different from 4. So this function as a function of psi in the variable in the unit disk is a holomorphic function taking values different from 4. So it is not possible that on the boundaries there is a set of positive measure where the function takes 4 as a value. So the Fatou extension of a holomorphic function does not take one value with positive probability, positive measure. So it is the same kind of generalization of the fact that a holomorphic map is not constant on a one-dimensional manifold, okay, in a sense. So you have exactly the fact that this representation rho of H of psi cannot have contain parabolic other than the identity, so other than for gamma is equal to the identity, and so this proves the claim. And now by theorem that I stated by Abikoff and Maskit, we know that we are in the other possibility, namely that the lenses of the representation tends to infinity, right? So let me just, yeah, I think my time is over. So in fact, when you use this fact and you use the equivariance of the map from the universal cover of B to the Teichmüller space, you see that, in fact, the length of the simple closed curve, of the image of a simple closed curve by a sequence of elements of the group that tends to infinity, the length tends to infinity because of that, because of the second step. I have no time to do that. So, okay, I'm going to stop. I'm sorry I was late. So thank you very much.